Hello, my name is Kevin Zhang, and in this video, I will be presenting my lab write-up on constant velocity. In terms of the structure of this video, I will first walk through setting up the realistic simulation, then the computational model, comparing the two and conducting an analysis, and finally, answering the reflective questions. All of this is to determine the main point of the lab, which is to analyze how Newton's first law regulates real-life movement. In deciding upon which model to simulate a constant velocity, I decided upon rolling a roll of tape, as its circular shape makes it more easily able to roll in a linear motion, and its smooth surface made it so that there are no arbitrary changes in velocity. Given its physical properties, it was an appropriate choice for the goals of this lab. After recording the video, I uploaded the video file onto Tracker where I set up everything in accordance to the week 2 videos. I chose the frame selection to be while the ball was already in motion so that we could ignore the initial net force resulting from us pushing the roll. I then set the point mass for each frame of the video and was able to generate a model as shown to the right. Having finished conducting the analysis of the real-life model, it was time to create a computational model. After importing the starter code to GlowScript, I had to modify the contents to accurately replicate the properties of my real-life model. This included modifying the radius, starting position, time cap of the while loop, and the velocity vector, which I calculated using this equation over here, delta x over delta t. With all of the modifications done, I was then able to run the program and generate my data for a comparison. From a glance, we can notice that the position graph is a straight slanted line, which makes sense given that the computational model is ideal. Furthermore, fundamental physical properties explain that because the position time graph is a straight slanted line, our velocity will be a constant line because the velocity vector is a derivative of the displacement vector, as depicted by this law over here. And since the derivative of a single variable function is a constant, so is our velocity. After finishing both models, I compiled their data to create a single time position graph with both models. The blue series represents the real-life simulation, while the dotted series represents the computational model. This is also noticeable simply by how perfect each line is. While both models are similar in the sense that they are mostly linear, meaning they both traveled at a near constant velocity, the computational model is objectively much more linear. And this is because the main difference between them is that while the computational model accounts for zero net force, it is unrealistic for the real life simulation to have zero net force due to frictional forces. One of the first things I noticed when comparing the two models on the same graph is that the real life model actually traveled further than my computational model, which is obscure because only the real life model is affected by friction, which would theoretically reduce the amount of distance traveled. I believe that this is because I chose two random points of displacement in time to determine the velocity for the computational model. Since the 2 points I chose were toward the end of the motion, the forces of friction had already slowed the tape's velocity, and thus my computational model used an overall slower velocity than the average. In order to improve this for future studies, I would use a true average velocity taken from the initial and final points. Over here, you can see what the velocities are. So 0.282 would be the true average velocity, while the velocity I used for the computational simulation was 0.273, which is a noticeable difference. So on to the reflective questions. So what if we changed the axes back when we were using Tracker? I hypothesized that if we were to flip the axes, very little would change. In fact, the only things that would change is the direction of our slope, which would simply be a reflection of its original form, as shown here. Other than that, however, the shapes stay similar as it is still mostly linear. As for the question of whether or not I can determine how many pushes and pulls are added together to give zero net force, it's difficult to say, but taking only into account the net forces in the x direction, the only forces are friction and air resistance, which both act in the same direction. Therefore, it is unlikely that there was actually zero net force. Thank you.